Heinemann Higher, Chapter 4, Trigonometry, Graphs and Equations. Next exercise at the end for J number 13. It's describing a siren's volume in a factory, where theta is the volume measured in decibels. Ambient noise in the factory is 75. So if you were to draw a graph of this, it would look like this. Well, first of all, that would be theta, being the volume, and that would be t, the time. It's starting at 70, so this sine is oscillating 70 up, and it's going up and down 20 in its one cycle. So going up 20 will take it to 90, and down 20 will take it to 50, and it's completing its cycle. I'll just do this in radians again because there's no mention, but I think possibly you can just do the question degrees as well, because there's no absolute values absolutely necessary. It's all relative. You've got 6 wavelengths by the complete cycle, so that must be 2 pi divided by 6, which is pi.3. Another thing is, it says if the noise in the factory is 75, which is just slightly above there. If the noise in the factory is 75, that means that the alarm would only be heard between these two parts, so it would only be audible for that blimp out of the whole cycle. Right, what does it say? A. Maximum and minimum volumes. That was easy, just did that. Because the max is going to be 70 plus 20, because the maximum sine gets to is 1, so 1 times 20 is 70 plus 20, so the maximum is 90 decibels, and the minimum will be 70 minus the 20, which will be 50 decibels. Well, that was easy. Next bit though. For what percentage of each cycle, because that's only a part of the time, is that going to be audible? Right, well that means I'm going to have to figure out what are these two times. When did it start and when did it stop being audible above the ambient background of 75? I'll need to find the times. So that's just solving that equation then. When does that equal 75? So B, I want to know when does 20 sine 60 plus 70 equal 75? 20 sine 60 equal 5. Sine 60 equals a quarter. 60 is inverse sine of a quarter. So 60 is going to be, and then you do inverse sine of a quarter. Well, I've done this in radians, and I've got 0.2526, call that 253. And that's going to happen when it's positive, so either here or here. So I've got two answers. I've either got it equals 0.253, or I've got pi minus 0.253. So I've got 0.253, 2.889, will I say. So t is going to be dividing them. So divided by 6 is going to give me 0.481, since I've got that one already. There's some decimal inaccuracy coming in here. It's 0.042, will I just say, for that one. So those are the two times, but I'm not actually interested in the times as such, it's the difference between them. That's why I could have had all these in degrees, I suppose. I've done it in radians now. So that to work out the difference in time, I've got 0.481 minus 0.042, which is 0.439. And finally, the percentage of the time is going to be audible will be that interval of time, 0.439, divided by the whole interval, which is pi upon 3, and then times 100%. And that gives you 41.92, etc. Or you could just call that 42%. It's audible for 42% of the time. And since I wasn't ever looking for absolute times, it was just relative times fractions, I could probably just have that in degrees then. Right, C. New regulations are introduced where it's got to be audible for 45% of the time. Was that 3% more? Right, what value of the amplitude? You've defined the new amplitude so that that interval there is now 45%, not just 42% of the time. Well, that means I have to work out that interval. So what is that interval of time? It's 45% of pi upon 3. Now again, since this is just relative fractions of a wavelength, it could be in degrees or radians. Since at no point am I actually going to need the absolute value of time. So for that part, what I've got 45% of pi upon 3 gives me 0.471, I'll just say, whatever the units happen to be. Then, if that's 0.471, that means that I've got, I don't know which pens to use here, I'll take a line down the middle of this. I know that if that interval there altogether is 0.471, then I know that time 1, for instance, will be that midpoint, which will be a quarter of that, so that's pi upon 12. That'll be pi upon 12 minus half of that interval, and the other time would be pi upon 12 plus it. I only need one value to feed into this equation here. So that'll be pi upon 12 minus a half of 0.471. 0.0262 I'll put for time 1. Then, I don't know this amplitude, I'll just call it A. So it's no longer 90 and 50, it's going to be 70 plus A, 70 minus A. But I know that A sine 6 times 0.0262 plus the 70 should equal 75. So that means A should be, take that away, is 5, divided by this thing here, which is just a number now, divided by sine of whatever that comes to, 0.157 I'll call it. So I've got, and that comes to 31.9622 and so on. So rounding that off to make it the same as the back of the book, I would have gone for 32.0, but 31.96 would have to be the new amplitude. Now at the back it says something like 31.96 degrees, but of course it's nothing to do with degrees because it's an amplitude, it's an actual value. That, if it had a unit at all, which it does I suppose, it would be decibels, because that theta is measured in decibels. Right, that was it in radian. You could have done it in degrees because I didn't want the actual absolute value of the time. It was all just to do with intervals and fractions of intervals of time. There.